Day 32, page 759, problem number 1. I'm going to use these three equations, or at least a couple of them, to show what we need to show here. Let's start with the basic magnetic field around a wire equation on the left-hand side here. If I solve for mu 0 over 2 pi, which is basically what we're starting with here, that is equal to B times R over I. So just looking at units here, this on the right-hand side, B is a magnetic field, is in Teslas, and R is a distance in meters, and I is a current in amps. So that's the unit, that is the unit for mu 0, because 2 pi has no units. Now we want to show that that is equal to a Newton per amp squared. So what I'm going to do is take one of the force equations over here and solve for B. I think the second one's actually going to work better than the first one. Let's see. You can use either one of them, but if I take the second equation for the force on a current carrying wire, B is equal to F over IL. So let's just look at units here for a second. The units for B are Teslas. So in other words, a Tesla is equivalent to a Newton per amp meter. All right. So now if I take that and plug it into the other equation on the left here, if I take that and plug it into T, I think it falls right out. Basically, I'll do this, I have a little space over this way. I'll have a Newton per amp meter times a meter divided by the amps. So what happens here is you get meters canceling out, and you have a Newton per amp divided by amp, and that is a Newton per amp squared, which is what we wanted to show you. I have kind of an awkward progression here, but that is what we wanted to show, that that is a Newton per amp squared.